This video is going to look at covalent bonding with a focus on dative or coordinate bonding. So let's work out, before we decide what is dative bonding, it's actually really important that we have a clear definition for covalent bonding, because a lot of students get this wrong. They just say it's sharing electrons, or they say it's bonding between non-metals. So a proper definition of covalent bonding is it's an electrostatic attraction, because all bonding is between a shared pair of electrons, so there is your sharing part, and the nuclei of the two atoms that are obviously sharing. So covalent bond, very different to ionic or metallic bondings. It's a very directional attraction. It's only happening between like these electrons and the nuclei either side. So this, for example, could be a hydrogen molecule where we just have a single proton in the nucleus and a single pair of electrons between them. So in a hydrogen molecule, that's not a dative bond, and the reason it isn't is because each of the hydrogen atoms would have had one electron to start with. So a dative bond or coordinate bond. So these two terms are interchangeable. I'm going to use the word dative bond for the rest of the video just so that I don't keep saying the words twice. You can choose whichever you find comes up most often in your exam board, or just whichever one you prefer, because they will be marked correct either way. So in a dative bond, this is where both the shared electrons come from the same donor atom. And we're going to get into that and look at what donates and what accepts and give some examples. The key thing to realize here, what's important, is that other than dot and cross diagrams or how they form, there's no other difference. So if you have the same two atoms, like nitrogen and hydrogen, and they are sharing a pair of electrons, you will have the same bond strength, because that is determined simply by the electrostatic attraction, and the electrostatic attraction is determined by what are the two nuclei and how far apart are they. They'll have the same bond length, because that is determined by exactly the same thing, which is what are the two atoms that are sharing. So basically it's only how it forms that makes it slightly different. And really, we teach it to teach students to understand some differences in how different bonds form. That's really what we're testing when we ask for dot and cross diagrams. So both shared electrons come from the same donor atom. So that means that we need two things, obviously, to make a dative covalent bond. We need one thing to have extra electrons, be an electron pair donor, and the other to be an electron pair acceptor. Very occasionally you may hear about electron pair donors being described as Lewis bases, but that's not really a common definition in most A-level specs. So what do electron pair donors need? They need a lone pair. So very common examples would be molecules containing oxygen or nitrogen, and here I've included ammonia and water because they very, very commonly come up, and you can see that both of them have lone pairs of electrons, or what we might call non-bonded or non-bonding pairs. So all covalent bonds have to be a pair. Okay, you cannot get individual electrons making up a covalent bond unless you're talking about like very recent scientific research, which has not really gone down into the A-level specification yet. So shared pair of electrons every single time. So the electron pair donor is often something like oxygen or nitrogen, and it could also be one of the halogens like fluorine or chlorine, etc. as well, because they usually have spare electrons. The electron pair donor could be a negative ion, but actually a lot of the time it's not. And then we need something that has a space. So we need something that has space to accept a pair of electrons, not just one. So not like a chlorine atom that just has space for one, but enough space to take 2 electrons from the electron pair donor. So a typical one is a hydrogen ion, and a hydrogen ion doesn't have any electrons at all. And in fact, other than in a gas state, H+ ions are always bonded to something. So when we talk about acidic solution, in reality, that hydrogen ion, which is just a proton, just a bare proton, is always bonded to a water molecule. And then another typical electron pair acceptor. So something like boron, and boron is in group 3, but it is a non-metal, so it's likely to share and do covalent bonding. And if it shared with something like chlorine or fluorine, it doesn't really matter what it's bonding with. It's only got 3 valence electrons, which means it can only share 3, which means there's always going to be this little space here where it has a deficiency, like it has an empty orbital. So it can accept a pair of electrons from something like a nitrogen or an oxygen or a chlorine. So there's that space. We're talking group 3, and also something like aluminium. Aluminium would typically class it as a metal, but aluminium is a little bit borderline and it can make some covalent molecules as well. So we've got hydrogen ions and we've got group 3 compounds with a little space. Those are very typical examples of electron pair acceptors. So let's have a look at the hydrogen ions, because as I said, it is really common that you would have to draw either dot and cross diagrams, or you would have to draw line diagrams to show the dative covalent bonding. So a typical ion is the ammonium ion, and the ammonium ion forms when you take ammonia, which is NH₃. So we can see that that's not charged because nitrogen has 5 electrons in its outer shell. You can see 5 dots in my dot and cross diagram, and the hydrogen each is contributing 1 electron. And we have this lone pair at the top of the nitrogen atom. So to draw NH4+, all I need to do is I need to add that hydrogen ion. Now hydrogen ion is just H+, which is just a proton, a hydrogen nucleus with no electron. So there it is. I'm literally just drawing hydrogen. You don't need to put the circles in, by the way. I will show some without circles. So there is my dot and cross diagram, and you can see that 3 of the bonds are normal dot cross formed by 1 electron from each atom, and then the 4th bond is a dative because it's showing the lone pair, and so both of those electrons came from the nitrogen. Now because this is an ion, every dot and cross diagram, even if it contains covalent bonds, if it has an overall charge, we put a bracket around the outside and we put a positive charge. If I wanted to show this as a more displayed formula, then there's my 3 hydrogen atoms that are normal covalent bonds, and then the only difference is I would sometimes draw an arrow to show from the nitrogen to the hydrogen, because the nitrogen is the donor and the hydrogen is the acceptor, and a square bracket and a positive charge on the outside. I've drawn that really small simply because I want to be able to show my next ion on the other side of this slide, which is H3O+, and literally same thing. So H3O+, you start with water. There's a normal water molecule. It accepts 1 hydrogen ion. So there it is, accepting that pair of electrons, no electrons in its outer shell. And we pop a little charge around the outside of it. And we could draw that HOH. These are also typical in, we could put a plus there, or we could put a plus around the on brackets on the outside, and one of them needs to be a dative, so I'll just make it that one. Doesn't matter which one you do. These sorts of molecules will also come up a lot in shapes of molecules. So for example, the ammonium ion, that's a tetrahedral shape because, as we said, there's no difference between that bond and any other bond. It's going to repel equally. So all of those 4 bonds are going to be equivalent to each other. So it's going to be a perfect tetrahedral shape, 109.5 degrees. Whereas your water molecule, that's actually going to be shaped like ammonia when it forms the H3O+ ion. If you want a name for that, that's called hydroxonium. You do not need to know that one. You do need to know the name of ammonium. So there's your H2O. H3O+ has 3 bonds and 1 lone pair, so that means it's just going to be trigonal pyramidal, and it's 107 degrees because that lone pair gives a little bit of extra repulsion. Okay, we could also get what we call dimer. So dimer, you may have heard the word polymer before, hopefully, which means many parts or many molecules joined together. So di means 2, so dimer means 2 parts or 2 molecules joined together. And so in the previous example, we had a whole molecule bonding to an individual hydrogen ion. So in dimer formation, you have 2 whole molecules joining together, like NH₃BF₃. So here's my BF3. Remember we said that because boron is in group 3, we've got that space just here where there is an empty orbital which can accept electrons, and ammonia has a lone pair, and so they can bond together like that. Again, like the other examples, I could draw this as a displayed formula. I'm not going to try and represent the shape because it's a little bit tricky because there are 2 central atoms. There is my fluorines. When we draw a displayed formula, we don't need to show the lone pairs. Sometimes we do if we're showing the shape of a molecule. So the only one that's different is that bond there. Notice also I haven't gone crazy with trying to work out multiple different dots and crosses and circles and triangles and stars for my electrons. It's really not necessary. So long as, for example, in my top diagram, boron is crosses because there's 3 of them, and fluorine is dots. And then in my bottom diagram, nitrogen is dots and hydrogen is crosses. So I've just made sure that every element that's bonding with something has a different symbol to the one that it's bonded to. Okay, and then another example of a dimer is going to be Al₂Cl₆. So this is with the NH₃BF₃, it was very obvious that you had a BF3 that had a gap and you had NH3 that had a lone pair. So this one's slightly different. So first of all, let's cut it in half because we know it's a dimer, and let's draw aluminium chloride. And I'm actually just going to rub out my diagram there because it's in the way. So aluminium chloride, you may see, looks very similar to boron fluoride because it's group 3 and group 7. So all of the outer electrons are going to look the same. And you've got the same situation where the aluminium has a space. But we're actually bonding it to another AlCl3 molecule. So we don't just have a simple donor of electrons. So looking out from the aluminium has the space. We can also see that all of the chlorines have lone pairs. So what we can do to make this dimer is we line up 2 aluminium chloride molecules. And here are my dative bonds. So this chlorine atom is donating one of its lone pairs to this aluminium, and this chlorine atom is donating one of its lone pairs to this aluminium. So we formed 2 dative bonds in order to join these 2 molecules together. If I wanted to draw it as a displayed formula, so one molecule looks like this. I'm going to line it up so that chlorine is next to aluminium and aluminium is next to chlorine. I need to make sure I get my arrows the right way around. So chlorine donates, aluminium accepts, and then this aluminium then just has 3 bonds to normal bonds to the other chlorine. Sometimes you'll see that on its side. I don't know why, like when it's drawn diagonally, it looks somehow like more complicated. It's really not that complicated. Okay, you see a space, you see a lone pair, and you line them up. Okay, speaking of complicated, I thought I'd put a couple of trickier examples in. So BeCl₄ this kind of thing comes up in shapes of molecules as well, and I don't know, people just get mad when there's a charge involved and get really confused. So like we did for the positive ions, if I saw NH₃+, I don't want to think, oh, it's a nitrogen that's sharing 4 electrons and then there's a positive charge. That's not how it worked. That worked because NH3 bonded to a hydrogen ion, which is a common ion that we see all the time. So what's happening with BeCl₄? Well, let's have a look at beryllium because that's a weird element to start with. That's in group 2. Okay, so that's only got 2 outer shell electrons. So when it comes to bonding to chlorine, all that beryllium can do, I'm drawing my own dot and cross diagrams now, rather than ones I've prepared earlier. This is what a neutral molecule of beryllium chloride would look like. It would be BeCl₂. Now beryllium, you might be thinking, hang on a minute, it's a metal, so is aluminium. Relax. If you're in that little top corner of the periodic table and you're near the metal non-metal line, then we're likely to be making covalent bonds as well as ionic, depending on the compound. So it shared 2 electrons. That is BeCl₂, which has no charge. And that is often a shapes of molecule question. It's a linear molecule because it has 2 bonds and no lone pairs. But so then can you see what I'm adding is I'm adding 2 more chlorines, but there's a 2- charge. So what I'm adding is 2 lots of Cl- ions. I mean, Cl- ions, they're as common as H+ ions, right? Chloride ions are everywhere. So chloride ions definitely have lone pairs. They literally have nothing but lone pairs, right? They have no bonds around them. So how would I draw a chloride ion? Well, I'll probably draw like cross, 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 dot, really. So it's a bit weird, this one, because if I just put that on, it's very hard to tell the difference between the beryllium dot and whatever this electron is, which is my negative charge. So what I might do is make it a circle. In this case, I might have 3 symbols for my electrons. Sometimes exam questions will specify exactly what they want you to do, so please read instructions. Sometimes it will say chlorine's going to be crosses, beryllium's going to be dots, and your negative charge is going to be some other symbol. So I'm going to move those chloride ions. I'm going to put 2 of them because there's 2 spaces in beryllium. It's only got 4 in its outer shell, so it has space to accept. So there. I tend to, when I draw my own dot and cross diagrams, when I'm not using PowerPoint to do it, I don't actually draw overlapping circles. I actually prefer to think of my atoms as little squares with 2 electrons on each side to make 8. You don't always get 8 in the outer shell, obviously, but it's a lot neater when you get complicated dot and cross. So that would be BeCl₄, but what have I forgotten? It's an ion. I need to do a square bracket. 2- around the outside. Okay, and another example that comes up relatively regularly is carbon monoxide. Just because it's a common molecule that is formed in incomplete combustion, they could ask about it. So if you had carbon dioxide, it would be just 2 double bonds. That sorts everybody out because oxygen needs to share 2, carbon is going to share 4. So when there's only 1 oxygen atom, the issue is that now the carbon doesn't have enough electrons. So I would start drawing it always with the premise that oxygen is going to form 2 bonds. Oxygen can't form 1 bond unless it has a negative charge because that would give it 7 electrons. And one thing you're definitely not allowed to do is you're not allowed to have an odd number. Okay, so I've done that. If I was to just leave it like that and then just put the rest of the electrons in, carbon would have 2 more, 4 in the outer shell. Oxygen is in group 6, so it would have 4 more. So oxygen's fine, like in terms of that has no empty orbitals, right? So oxygen has, in this situation, 8 electrons around it. But carbon has 6, so this now has an empty or an unoccupied orbital. And oxygen has lone pairs. So we can just move that into the empty orbital of the carbon atom. We're going to make essentially a triple bond. So I'm going to redraw it, cross, dot, and then 2 dots to show the dative bond. That means oxygen's got 1 lone pair left and carbon's got 1 lone pair left. If I was drawing it in terms of line diagrams, C, normal bond, dative bond from oxygen to carbon. That's really messy, sorry. And I could put the lone pairs either side if I wanted to. There we go. Okay, the ultimate dot and cross diagram, I think, certainly for A level, is going to be our HNO₃. So I feel like I could not make this video without explaining what's going on. And by extension, we are also going to do the nitrate ion. So HNO₃, let's have a look at this guy. Whew. So nitrogen is in group 5. Excellent. So we've got 5 electrons. Now, nitrogen cannot share all 5 of them. So what I'm going to put here is nitrogen has a maximum of 8 in its outer shell. You might be thinking, well, yeah, duh, obviously. No, it's not obvious, actually. So nitrogen is in period 2, which means it's 1s2, 2s2, 2p3 is the electron configuration. So there are 3 spaces in its orbitals. Okay, if we drew the p orbitals, we've got like 3 unpaired electrons, which is why it shares 3 electrons. The reason I say it's not obvious necessarily that it can only share 3 is because actually phosphorus can share all 5 of its electrons, because phosphorus is in the next row down. So phosphorus's outer electrons are in the 3rd shell, and the 3rd shell has space for more than 8 because of the d orbitals. So in this situation, don't always assume that 8 is the maximum. Period 2 elements like nitrogen, oxygen and carbon, which do come up very regularly, they can only have 8. So that means oxygen usually needs to share 2, nitrogen needs to share 3, and hydrogen needs to share 1, and this just does not work. Okay, so whenever you get something like this, first thing you need to do, nitrogen goes in the middle because it does have the most electrons that it can share. Oxygen has options of a double or single bond. Now, H is going to bond to oxygen. Okay, the last thing I want to do is put hydrogen on the nitrogen, because then the nitrogen is going to have even less room for those 3 oxygens. So I'm going to draw this as a line diagram first to see what would happen. So if I do a single bond with oxygen and a single bond with hydrogen, this one is good and this one is good. Okay, so right now I've used 1 of nitrogen's electrons, I've got 4 left. Okay, I'm going to put a double bond to an oxygen, because let's face it, an oxygen would rather have a double bond. Okay, and also because I happen to know that HNO₂ is another molecule that exists. Okay, so that at the moment I've now used 1, 2, 3 of my nitrogen electrons. Now that's it. Nitrogen is not allowed to share any more electrons in a normal bond. It has a lone pair now. If I try to add any more electrons around that nitrogen, for example, by making a double bond with oxygen, I can't do this. Even though the oxygens are fine, the nitrogen is not fine, because that's now got 10 electrons in its outer shell, because it's got every single one of those bonds, remember, is a pair. So we're not allowed to do it like that. So what we're going to do instead is donate this pair of electrons to an oxygen, because actually oxygen does have a little space around it. So I've mixed my diagrams, which I always tell students not to do. So this would be how you do it in terms of a displayed formula. One single bond, one double bond, one dative bond. Now let's draw it as a dot and cross. Oops, I'm going to do it over here. So double bond. Put the bonds in first. I like to draw my lone pairs as both dots. So that means this is going to be, so that's got 6 electrons left because it accepted 2 from the nitrogen, it's not sharing any. The oxygen on the top is using 2 of its crosses, because nitrogen is dots, in the double bond, so it has 4 left. The oxygen on the right hand side is using 1 there, and it's got 1 bond to a hydrogen, and then the rest, the other 4, will be crosses. So that's the molecule that hasn't got a charge, everything's got the right number of electrons. To make an NO3- ion, which is a nitrate ion, all I've got to do, how does that form? Well, it forms when it loses the hydrogen ion. It loses this H as a H+, and because it goes as an H+, it leaves its electron behind. And so I just draw exactly the same ion. And that's a good tip for anything if you're drawing sulfate, nitrate, carbonate. Just remember that the way that it formed was by losing H+. So there we go, I just draw it like that. Square bracket and a charge. And that's the nitrate ion. In reality, so in some specifications, or if your teacher is a bit extra, you may have learned that in reality, although it looks like double bond, single bond, single bond, the electrons actually delocalize around this structure. You have something called resonance structures, because actually if you've got 3 identical atoms, 3 oxygens around the nitrate, actually they will all behave the same, and that extra pair of electrons will actually just get moved around the structure so that it spends equal time with each oxygen. But you don't really need to know that at A level.